In this lecture, you're going to learn about how to determine the stereochemistry for two chiral centers. So far, we have done one. So if you have two chiral centers, then what is the relationship? How many isomers can you get, and so on. And then we'll also talk about cyclic structures.
So far, we have been dealing with compounds that have only one chiral center. Now let's look at compounds that have two chiral centers. Remember, we can have compounds which can have up to 9 or 10 chiral centers. That was one of the examples that we did. So molecules can have more than one chiral center. So if you have two chiral centers, then each of those chiral center is going to have its own pair of enantiomer. The enantiomers are mirror images. The other pair of compounds are actually called diastereomers. They have no optical relationship whatsoever. Okay, enantiomers will rotate the plane polarized in opposite direction, but diastereomers have no such relationship. Okay, and so they're just called stereoisomers for that reason. But very specifically, they're called diastereomers because they're coming from the same compound, but they're not mirror images, okay, of each other. The number of isomers that are formed according to the number of chiral centers is 2 to the power of n. N is the number of chiral centers that you have. So for example, if you had only one chiral center, you would have two stereoisomers, which two of them are going to be the enantiomers. If you have two chiral centers, then the number of stereoisomers you will have is 2 to the power of 2, which is 4, which is perfect because each of the chiral center is going to have its enantiomer. So you have 4 compounds. If you have 4 stereoisomers, then of course the relationship between two of them is going to be that of diastereomers and some of enantiomers. If you have 3 chiral centers, that's 2 times 2 times 2, and that is 8. So you have 8 compounds or 8 isomers. So it gets more and more and more. The more chiral centers you have, the more stereoisomers you have. In some cases where we have symmetry in the molecule, then that compound is not optically active. In case of one chiral center, we did not have that issue because there was not that big of a molecule to have any kind of a symmetry. Okay, but as the molecules get larger, then some kind of symmetry can be possible, and if there is symmetry in the molecule, then that compound is not optically active, which means it is called achiral. So let's look at this compound over here, okay, which has two chiral centers. So compounds 1 and 2. Okay, so let's look at these two first of all. And 1 and 2, these are mirror images of each other. Okay, you have 4 carbons, 1, 2, 3, 4. And in the middle two carbons, you have bromines, okay, attached to it. So this is one set of enantiomers. And then in the other 3 and 4 case, we have flipped one of the bromines, which means that what you did is you actually broke this bromine out, took it there, took out the hydrogen, and put it in place of the bromine. You did not do a rotation because the location of the CH3, the methyl group, did not change. So you did not rotate the molecule, okay? You actually literally broke the bond bromine from here, put it over here, and put the hydrogen over here. Once you did that, now this compound is the mirror image of number 3, okay? So 3 and 4 mirror images, 1 and 2 mirror images. So 1 and 2 enantiomers, 3 and 4 enantiomers. However, 1 and 3 are diastereomers, 2 and 4 are diastereomers, 2 and 3 are diastereomers. Okay, that's the relationship between diastereomers, which means they're not mirror images of each other, but they're still related, okay, in some ways. So diastereomers are stereoisomers of the same compound, but not mirror images. The nice thing about diastereomers is that they have different physical properties and they can be separated out. Remember, we mentioned that enantiomers have exactly the same physical properties. You can't separate them out. Okay, it's very, very tough to separate enantiomers, but diastereomers have different physical properties. So it's actually a little bit of an advantage to have diastereomers. Okay, looking at the same molecule, okay, the same one where you had 4 carbons and the 2 bromines in here. In some cases, we end up having two chiral centers, but not enough stereoisomers, okay? And the not enough stereoisomers meaning to the power of n, as we were talking about before. So which means that a molecule that has two chiral centers should have 4 stereoisomers. Well, it turns out that this molecule actually has only 3 stereoisomers. And how does that come out to be? And that is because this molecule C and D, okay, they can actually be superimposed on each other. Okay, so if you take this molecule out of the plane D, if you take D out of the plane, flip it 180 degrees, you should be able to superimpose it on C. Okay, and so that's why if it is superimposable on each other, it's not optically active, it's not chiral. These kind of compounds are called mesocompounds. So even though they have a chiral center, they still are not optically active. Okay, and so they're called achiral. Okay, and it doesn't mean they don't have a chiral center. They do have a chiral center, but they are not optically active. And the other way of looking at this molecule and trying to figure out if it is going to be a mesocompound or not, or whether it is optically active or not, is by looking at the plane of symmetry. Okay, and so if you look at this molecule and just slice it into half and just fold it on top of each other, you will see that it actually has a plane of symmetry. Okay, so each atom here, bromine is on top of bromine, hydrogen on top of hydrogen, and methyl group on top of methyl group. So it has a perfect plane of symmetry. And these kind of compounds are not optically active. Again, these are called mesocompounds. Naming more than one chiral center, the process is still the same, okay, because you still have the chiral center. You still have to figure out which one is the lowest priority. But the thing is that you don't have to forget this part, okay? Don't forget this part over here. You consider this as a huge group, okay? You have to consider this also. So hydrogen here has the lowest priority for carbon number 1 here. So bromine highest priority. Then this carbon is a second priority because this carbon is attached to a carbon and a bromine and a hydrogen. This carbon is just a methyl group, okay? So this has third priority, and then hydrogen is lowest priority. So you look at this hydrogen, keep it at the back, okay? This one, keep it at the back. And then your bromine has the highest priority. Then this group over here, okay, which is over here. And then the CH3, okay? You still have the same process of keeping the lowest group at the back, okay, away from you, and keep all the other groups facing you, okay, from your eye. And so that's how you see it, okay. Then after you're done with one designation, then you look at the second carbon, okay, and now you have this hydrogen, the methyl group, bromine, and all of this. It'll have the same kind of priority in the sense that it has the same atoms, okay. And so the important thing is keeping the lowest group at the back and looking at this group as a whole, okay, and not breaking it apart, okay. And so bromine, again, highest priority, and then the CH3Br, and then finally the methyl group, okay, that's your priority. So in this case, they happen to be RR configuration. It may not always be the case, but this one is RR, okay. So the enantiomer of this is going to be SS, okay, that's what the designation will be. The diastereomer of this would be RS, okay, or SR. That would be the diastereomer. Here are some examples of diastereomers, and in this case we actually have rings also, okay, because so far we have not really quite worked with rings. So here we have 2-methyl cyclopentanol, which means that there's an alcohol group and there's a CH3 group, okay. And in case of the CH3 and the OH, you can have 2 relationships because they have 2 H's. You can have cis relationship and you can have trans, okay, relationship. So here these 2 are enantiomers, okay, these 2 groups over here, these are these 2 compounds, these are enantiomers. And then if you have trans, these are also enantiomers. Why are they enantiomers? These are enantiomers because they are not superimposable on each other, okay. So that is for 2-methyl cyclopentanol. And then we have the 1,2-cyclopentadiol, in which we have 2 alcohol groups. The difference between this first example and the second one is that in this case, in the diol example, you have two alcohol groups. Okay, in the first example, you had a methyl and an alcohol, two different groups. But here you have similar groups. So if you have similar groups, there is a chance that there's actually symmetry in the molecule. So in the cis molecule, there's actually a symmetry, internal symmetry over here. So this is only one meso compound. Okay, it's not an enantiomer, it's a meso compound. The trans, however, is not superimposable, and this is a pair of enantiomers. These diastereomers that are listed over here, this is actually for each other, not between the two molecules, but the relationship between the cis and the trans 2-methylcyclopentanol, these are diastereomers, and then the relationship here between the cis cyclopentanediol and the 1,2-cyclopentanediol, which is trans, these are diastereomers. Okay, so enantiomers are mirror images, diastereomers are not mirror images. Six-membered rings, they can also be optically active depending on how the groups are arranged. One of the things that I suggest for trying to figure out if six-membered rings are optically active or not is actually to build them. Okay, build two of the rings and then try and superimpose it on each other. Okay, and see if they do or not. Because if they do, obviously, then they're not optically active. But if they don't superimpose on each other, then they will be enantiomers. Okay, and so sometimes it's hard to look at a molecule and see if there is a plane of symmetry or not, or internal symmetry or not. In this case, it's very easy to see when you have the 1,4-dimethyl because they're completely opposite each other. So yes, you can see the plane of symmetry in the 1,4 also. Here trans, you can see the plane of symmetry. It's easy to see. In some cases, it's not so easy to see. Okay, so for example, in the 1,3, it may not be that easy to see, but this one does not have a plane of symmetry. It might seem that, oh, look, you know, they can superimpose on each other. I can just flip this molecule, I can fold it, but it's not. Okay, and so the cis may have a plane of symmetry, but the trans does not. So one of the best ways to do this is to actually build a molecule and then see all these rings, okay, and see if they actually superimpose on each other or not. One way of representing structures is called a Fischer projection. We learned a little bit about this in conformation analysis also. Fischer projections are very common in carbohydrate chemistry because Fischer is the chemist who kind of developed that whole chemistry and how to write structures in carbohydrate chemistry. Structures in Fischer projections are represented as 2D structures, okay, as you see on the right here. And these structures don't really tell you what is going to the front, what's going to the back. It's kind of understood, okay? It's understood that whatever is horizontal is coming out of the plane and whatever is vertical is going behind the plane. The middle two carbons are in the plane, all right? So the side bonds are always coming out at you and the one on the top and the bottom are going away from you, okay? Look at only two carbons at a time because if you do more than that, then you'll get confused because for this carbon which is going behind, if it has another carbon attached to it, it will be going further behind, okay, and so that will get really confusing. So the best thing to do is look at two carbons at a time when you're trying to figure out what the chirality is. Here is a nice chart, okay, of everything that we have done as far as isomers are concerned. So compounds that have the same molecular formula, okay, you can have two different kinds. You can have constitutional isomers, you can have stereoisomers. If you have just rotation going on, then you have conformation isomers, okay, and conformations we've already done before, and conformation pretty much ends over here, okay, because in conformation you can have anti and eclipsed, and then you have the two-chair conformations as far as the cyclic compounds are concerned. So that's conformational. And here when you have the same kind of molecular formula, you can have constitutional isomers or stereoisomers. Constitutional isomers are different because they're different structures. But when you have stereoisomers, then you can have two different kinds of compounds, okay, which means that something that has no chiral centers, sometimes which has chiral centers. So for example, cis and trans, this is with double bonds, okay, and so they have no chiral centers, but they're still stereo compounds, okay. They're called geometric isomers sometimes, and they can also be called diastereomers. If you have chiral compounds, or if you have chiral centers, excuse me, then you can have enantiomers, you can have mesocompounds, and you can have diastereomers. So if you have only one chiral center, it's an enantiomer. If you have more than one chiral center, then it can be achiral because it is a mesocompound. If it is chiral, then you have two kinds, which is a diastereomer and an enantiomer. All right. Remember, a diastereomer can also be a mesocompound. It depends. So this is a nice chart to keep handy. And here's another little chart to see if your compounds are stereoisomers or not. Okay, and if you have two not of the same molecules, then do they have the same molecular formula? If they don't have the same molecular formula, they're not even isomers. If they have the same molecular formula, great. Do they have the same kind of structures or not? If not, they're constitutional isomers. If yes, they have the same structure, then they're stereoisomers. Okay, then you have to see if they are cis or trans or R or S. And then if the molecules are mirror images, no, then diastereomers. If yes, then they are enantiomers. So this is a nice little chart also, flow chart, to help you figure out if you have same or different kind of molecules. I think this is probably one of the least used chart, okay, because there are easier ways of doing this.
Your keywords for this presentation, well, what I have done is I've put a lot of keywords over here because you've done a lot, and I thought this would be a nice review for you to have all the keywords here. Make sure you learn all these words and understand their meaning, because we have done all of them, whether something is a chiral center, chirality, and these words keep coming up again and again. Okay, so make sure you learn what all these words are. That's your keyword list.